Hello everyone, this side Dr. Isha Mehra from ABES Engineering College. Today in my presentation, I'm going to do few numericals of optical fiber. It's important for any kind of competitive exams. So without any delay, let's start. The outlines will be simple optical fiber formulas we're going to discuss and their numericals. So there are few formulas for optical fiber. The first one is the numerical aperture. So the numerical aperture of the optical fiber is given by under root of n1 square minus n2 square. The theory part I have already explained in my last presentations. So for any doubt, you can go through those presentations as well. N1 here is the refractive index of core. N2 here is refractive index of cladding. So let's start with an easy numerical this time. A silica glass optical fiber. A silica glass optical fiber has core refractive index N1, which is 1.5, and cladding refractive index N2, which is 1.450. 1.450. Always we have to remember and we should know that refractive index of core is greater than refractive index of cladding. Maybe in your exam, it's not mentioned what is N1 and what is N2, only refractive index will be there. So we have to figure it out, which will be the refractive index of core, that is which one will be N1 and which one will be N2. So here we have to calculate, we have to find the numerical aperture. So what is that numerical aperture? NA, numerical aperture, will be given by 1.5 square minus 1.450 square. So the numerical aperture in this case will be 0.385. There will be no unit in this case. Coming to the next question, we have to calculate the numerical aperture as well as the acceptance angle. So acceptance angle is another formula. Calculate numerical aperture and acceptance angle of the optical fiber. In this case, N1 and N2 is again given to us. N1 will be 1.48 and N2 will be 1.46. So numerical aperture will be simple. Under root of 1.48 square minus 1.46 square, which comes out to be 0.2425. Acceptance angle in this case will be sine inverse of numerical aperture, that is sine inverse of 0.2425, which will come out to be 14 degree, right? So we have done two basic numericals right now. One is for numerical aperture and other is for acceptance angle. Now coming to the third part, third question, let's see what we have to calculate. And optical fiber has N1, that is core refractive index, which is 1.36, N2, which is cladding refractive index, that is not given to you, so we don't have to bother for it. What else is given? Yes, in this case, the fractional refractive index is given. And what is fractional refractive index? It is given by n1 minus n2 by n1, and here its value is 0.025. It is basically the relative ratio which is given by n1 minus n2 by n1. So here its value is 0.025. We have to find the numerical aperture as well as the acceptance angle. So Na means the numerical aperture, which is given by under root of n1 square minus n2 square. But the problem is here that n2 is not given to us. So there is one more formula. Na is given by n1 under root of 2 fractional refractive index. On solving this, Na is 1.36 under root of 2 into 0.025, which comes out to be 0.304. So this is your numerical aperture. If we talk about acceptance angle, it will be simple sine inverse of numerical aperture. So it will come out to be sine inverse of 0.304, which will be around 17.7 degree. So this is, we have calculated acceptance angle and numerical aperture. Coming to the next question. What is that next question? Calculate calculate fractional refractive index for a step index optical fiber having core and cladding refractive indices as 1.55 and 1.50 respectively. So we know that fractional refractive index is given by n1 minus n2 by n1. So it will be 1.55 minus 1.450 by 1.55. So this will come out to be 0.032. So we have done till now three formulas. One is numerical aperture, other is acceptance angle, and the third one is fractional refractive index. So moving further, this time one more thing we have to find out, that is the critical angle. So let's write the question. Calculate numerical aperture then acceptance angle and critical angle this time of the optical fiber, which is having N1 as 1.50, N2 as 1.45. So in my previous question, we have used these data for numerical aperture and acceptance angle. So again, we can go for it, or we can use some different formula this time for numerical aperture and acceptance angle. We have numerical aperture given as under root of n1 square minus n2 square. We are going to use the formula. It will be 1.50 square minus 1.45 square. So the numerical aperture will be around 0.385. Acceptance angle will be simple sine inverse of numerical aperture. So it will be sine inverse of 0.385, which comes out to be 22.6 degree. And the critical angle phi c, it will be sine inverse of n2 by n1, that is sine inverse of the ratio of refractive index of cladding to the refractive index of core. So it will be sine inverse of 1.45 by 1.50. So its value will be 75.3 degrees. So like this, we have calculated critical angle as well. Let's do some different question again. The fractional refractive index is given this time. So what is fractional refractive index? It is 0.0135. 0.0135. It is given in the question. And numerical aperture is also given. What is numerical aperture? Here in the question, it is 0.2425. But we have to calculate. We have to calculate refractive index of core as well as refractive index of cladding. It's simple. We have numerical aperture in terms of fractional refractive index. Fractional refractive index, it will be n1 under root of 2 delta. So delta is given to you. We can easily find n1 because numerical aperture is 0.2425. n1 we don't know, but we know what is fractional refractive index, 0.0135. So n1 will be around 1.476. Using the concept of fractional refractive index, which is n1 minus n2 by n1, we can easily find what is n2 because now n1 is known to us and fractional refractive index is also known to us. So this will come out to be 1.456. We can cross check this and we can see that 1.47 is greater than 1.45. So this is okay because refractive index of core is greater than refractive index of cladding. Now coming to a very different concept of the optical fiber numericals. So first I'm writing the question. A step index optical fiber, if you want to go through the types of optical fiber, so in the previous presentations and videos, you can go through it. Already everything is explained in that slides. A step index optical fiber has core refractive index N1, which is 1.466, and cladding refractive index, which is 1.460. The wavelength of the light in this case is given. Lambda is, or wavelength of the light is 0.85 micrometer. Here in this case, we have to find out the normalized frequency, which we also called as V number. Find the normalized frequency or V number. And the number of modes the fiber supports. That is the maximum number of modes we have to find out. So the V number or the normalized frequency is given by 2 pi r by lambda under root of n1 square minus n2 square. On putting the values, we are going to get 2 pi. Yes, the diameter is also given in this case. I forgot to write. So the diameter of core in this case is 50 micrometer. So the radius will be 25 micrometer, it will be 25. I'm not changing it for any other unit because in numerator it will be in micrometer, and denominator also the wavelength is in micrometer, that is 0.85. So no need for any conversion. Under root of 1.466 square minus 1.46 square. So the V number or the normalized frequency come out to be 24.75. The maximum number of modes and max in this case will be V square by 2 because this is a case of step index optical fiber. So it will be V square by 2, 24.75 square by 2, which comes out to be 306. So the maximum number of modes the fiber is supporting is 306 in this case. Doing one more question. The core diameter is given in this case. So what is core diameter? It is 70 micrometer, and relative refractive index difference in terms of percentage, this time it is given. It is 1.5%. Wavelength, the operating wavelength in this case is given as 0.85 micrometer. Refractive index of core in this case is given 1.46. And what we have to calculate now? So we have to calculate couple of parameters. First is refractive index of cladding, that is N2, which we also call as refractive index of cladding. Then second part, we have to calculate normalized frequency, which is V number. And the third part is the maximum number of modes, N max. So coming to the first part, we have fractional refractive index, which is 1.5 by 100. That is N1 minus N2 by N1 is given. So on solving, we are going to get N1 minus N2 as 0.015 N1. On solving this, we are going to get N1 and N2. So N2 in this case will be 0.985 into 1.46, that is 1.438, because N1 is known to us, right? N1 is 1.46. So we can easily find out what is N2. Then in second part, V number, the formula of the normalized frequency, I have already told, it is 2 pi r by lambda under root of N1 square minus N2 square. Everything is known to us. Radius as well as wavelength as well as refractive index of core, refractive index of cladding. So on solving and putting the values, we are going to get the V number as 65.42. And the third part, which is the maximum number of modes, again it is a step index optical fiber. So the maximum number of the modes which the fiber can support, it is V square by 2. So it will come out to be 65.42 square by 2. So this will be 2139 modes. So maximum number of modes are this one. So a quick revision that what the formulas we have done. We have done the numerical aperture, which is under root of N1 square minus N2 square, acceptance angle, which is sine inverse of the numerical aperture, then fractional refractive index we have talked about. Also, we have talked about the critical angle, sine inverse of N2 by N1, then V number, which is the normalized frequency given by 2 pi r by lambda under root of n1 square minus n2 square. Then maximum number of modes which the fiber can support. In terms of step index, it is V square by 2. In terms of gradient, it is V square by 4. So these are few questions which we have done. These are the references: optical fiber communication by Keyser and optical fiber communication principles and practice by John M. Senior. This is a disclaimer. Thank you. Thank you all.